All right, so good morning, everyone. Today we are going to carry on with our discussion of analysis of algorithms. Can you hear me? If you can quickly maybe write down yes or Ronak. Okay. Yes, perfect. So, all right. So last time we looked at how, for example, we are trying to perform a task. We can do it in multiple ways. We looked at binary search, and we said that the binary search is a methodology of searching for something, right? We can do a linear search where we start searching for a particular value and we go through the complete list and find out where it is lying. Then second, if we, for example, save things in a organized way, organized way, in that case, we can actually create strategies with which we can perform, for example, the searching task much more optimally than what we were doing over here, right? And we looked at one of the such algorithms, and this was called as binary search, right? And in binary search, like for example, in this previous case, we had this is our space where we have to search and we were going linearly. But in case of binary search, we had the same space, but in place of finding out things in a linear fashion, we divided into smaller parts and quickly we moved from one to the other, and everything became faster than what we were doing over here, right? For example, in this case, if we had n items, and in this case also we have n items. In the first case, in the worst case scenario, right, we have to be very careful about this worst case scenario, right? Scenario. Uh, in this case, we had to make n comparisons to find out where that particular entry exists, whatever we are searching for. Whereas in this case, so this was for linear search, right? Whereas in this case, this came out to be log n, right? And we know that log n is far easier, or the number of calculations decreases very drastically or exponentially if in place of n we use log n. Why? How do we know that? So suppose, for example, if there are 10 items in and you have to search for these 10 items, there are these 10 items, right? If you are doing linear search, you have to perform n comparisons, whereas in this case we have to perform log 10 base 2 is going to be always less than 10, right? So we can see that we have reduced the number of calculations by performing an intelligent or structured way search in place of performing a linear search, right? In place of performing linear search. So these strategies, but there was a catch in this, that if we want to perform a binary search, then we have to have our data stored in sort. We have to have our data which is organized, right? In case of binary search, this organization was that we have our data sorted, correct? If the data is sorted, we can perform binary search, and this is going to help us in doing less number of calculations than what we were doing initially. So this is what we say, we call as different strategies of performing the same task faster than what we were doing initially. Now let us move a little bit forward and try to find out what else can we do. Okay. We So to find out, for example, in the previous case, we were using n searches, and then we utilized binary search. We had to do, or we had to perform only log n searches. So there was a big difference between the two. Now, why are we using this n and log n? Because we also discussed yesterday that the if we find out the execution time in terms of in terms of in terms of time, which is like seconds or hours, etc., then this is not a good methodology of finding out how our algorithm is doing. Can any one of you tell me why calculations or the giving us how much time a particular algorithm takes in seconds and hours is not a good strategy? Anybody? We are saying that in the first in the we are going to take, yes, different speeds of computer, right? Because the hours or seconds, etc., depends on the configuration of individual computers. On one computer it may take 10 seconds, in another computer it may take 1 hour, because it is all depends on the type of computer we are going to utilize. Yes, it will depend on specifications of computers, absolutely right. So in place of doing this, we said that we are going to utilize something else, which is how our algorithms execution time behaves with respect to the input, right? So in the first case, as the input grows, number of comparisons are going to linearly increase. In this case, as the input increases, the number of computations are going to increase with log n. What does it mean? We will soon see in today's lecture and tomorrow and whenever we have the next one. So the way or methodology to find out or to depict an algorithm's execution speeds, or its way of how much time it is going to take, is called as big O, right? Big O is Landau's symbol notation, is a special notation that tells us how fast an algorithm is, right? So this is also a kind of measure of speed, but yes, not in terms of time, but in terms of the input which we are going to provide to our algorithm, and it makes a big difference, right? So for example, if linear search takes n number of comparisons or executions, binary search is going to take only log n. And if we draw it, n is like this, and log n is something like this. So you can see that as n increases, this is our time, as n increases, the execution time increases very fast. This is n, this is log n. Whereas if we use binary search, as n increases, or the number of items within which we have to search for an item, it is increasing far more slower than what it was doing with n, right? So this means that we have to find out a strategy with which we can compare these two things, and this is called as big O notation. So please understand that big O is a way to find out how fast our algorithm is, right? So big O is a way to find out the execution speed for a particular algorithm when we look at the input size. Any questions? Anyone? Okay. Do you Should we say execution speed? So I have got two questions. Let me first answer the first one. Should we say the execution speed? Uh, uh, we can, but we should remember that speed is something which depends on time, right? And this big O notation has nothing to do with time, correct? Big O is only a way to compare, right? It is going to tell us how fast an algorithm is when compared with some other methodology. So big O, for example, if we say, big O is only going to tell us how fast our algorithm is with in comparison to the input sizes. So when we say how fast, we are saying that if we provide n inputs and if we provide n minus m inputs, how our algorithm is going to behave. So for example, if n minus m is less, if we look at this particular graph, and if, for example, we are trying to perform linear search, we can only say that n minus, suppose this is n minus m, and this is n, we will say that if we perform linear search, this much amount of time it is going to take. And if we perform n minus 1 searches, then it takes this much amount of time. Whereas if we does n searches, it is going to take this much amount of time. At the same time, if we do use binary search, then it is going to take this much amount of time. If we do for n, it is going to take this much amount of time. And this time is not in seconds at all. So as n grows, we are going to say that the time requirements are going to grow like this, or they are going to grow like that, right? In this case, the requirements are increased much more slower than what they do, for example, if we use linear search. So we can say execution speed, but we should remember that it is only a notation to relatively find out how our algorithm is going to work as we increase the number of inputs, right? So big O notation is a relative representation, right? Please remember, this is very important part, that big O is a, let me write it down over here. Big O is a uh, relative representation of complexity of an algorithm, right? We are trying to find out how the complexity increases as we increase the input size, right? So you will be able to understand. Wait for one or two more examples, and then things will become slightly more clear. Otherwise, we'll come back and look at it again. Any other question? All right. So let's here is an example, and then will be a question which you should try to answer, and then we will obviously find out the answer ourselves also. So Bob is a guy who does a mental test that 100 items through linear search takes 100 milliseconds, right? 100 items takes 100 milliseconds. uh, sorry, 7 milliseconds. Let me just, right? It takes 7 milliseconds with binary search. So it is, and for obviously for regular linear search, how much time it is going to take? 100 milliseconds, right? So if we use binary search, if Bob uses binary search, he is going to take 7 milliseconds, and with linear search his algorithm is going to take 100 milliseconds. So he thinks that binary search, or he calculates mentally and he says that binary search is approximately 15 times faster than the linear search, right? Now Bob runs binary search with 1 billion elements, and it takes 30 milliseconds. 30 millisecond into log 2n, so it takes 32 milliseconds, right? With binary search, and is about 15 times faster than simple search, because simple search took this and this. So he says that if I perform linear search on 1 billion elements, it is going to take 450 milliseconds, right? Which is, and for example, to run his algorithm, he has 10 seconds, and he finds out that if I use binary search, it is going to take 32 milliseconds. And if I do linear search, from this mental calculation, he says that linear search is going to take 400, approximately 450 milliseconds. Now, you have to tell us whether it is and Bob decides to go with a simple search, because he doesn't have to do anything at all. One by one he'll compare amongst the elements, and he will find out that here is my item. So you have to tell us whether it's a right choice for Bob or not. If yes, why, and if no, why. Okay, no, it is not correct. All right, can you maybe in few words, if you can write down if it is why it is not correct choice, and others also please write down why it is not a good choice. This calculation is wrong. All right, this calculation is wrong. Can you tell me the reason why this calculation is wrong? No, because it is not linear graph. Absolutely right. You know what he has done is not correct. N log n value is not constant in increase with n. Wrong choice. No, because it may not be worst case for which he got the results. Wrong choice because the relation is not always 15 times due to log base 2 and linear graph. All of the answers are right. So this indicates that maybe either you knew it already or I was able to put my message across. I don't know. But all of you are right. In linear search, it takes n time, and in binary search, it takes log n time. But the conclusion which he made was direct relationship for a particular example, which means that n is kind of directly proportional to log n, which is not true, right? Therefore, the basis of his judgment is wrong. Therefore, the calculations which he has made over here are also wrong, since time complexity of binary search and linear search are not proportional. Right, this is exactly what one of our friends has told. So this is not correct, as I wrote down over here. There is no direct relationship, and therefore his choice is not correct. Now can you tell me in place, so he said that binary search will take 32 milliseconds, correct? And therefore he said that it is going to take 450 milliseconds, which is wrong. Can you give me an approximation? How much time will it take? Any approximation, I mean. Yes, right. So it is going to take 1 billion seconds, which is like, let us, let me just quickly go to the answer, and, so that we can have a look at it. Here it is, right? So a simple search takes 100 milliseconds. Binary search takes 7 milliseconds. We have more answers coming. 1 billion seconds, absolutely correct. What you are saying is absolutely right. It is going to take 1 billion seconds. And for 10,000 elements, it is going to take 10 seconds. This is going to take 14 milliseconds. Things are in control. And as soon as the elements become 1 billion, this simple search is going to take 11 days, right? 11 days. Whereas our binary search is going to take only 32 milliseconds. So you can see, now I think you will be able to appreciate the advantage of binary search over simple search. As the input size is growing, you know there is a mammoth increase in the time requirement for our simple search algorithm, whereas for binary search this guy is increasing very very slowly, logarithms, by the logarithm rule. So binary search is obviously extremely good if our input size is increasing exponentially. For example, if he wanted to search maybe within 10,000 elements, he could have used this or this, both of them. This is still is only 14 milliseconds, so this is far more better than what simple search is. But still, if he needs to perform some calculations within or approximately 10 seconds, he could have chosen simple search. But you can see with the tremendous increase in the input size, the time requirements for binary search and simple search are moving in completely different directions, right? So, this is the reason why we are looking for some methodology which can compare how our algorithm is going to behave when we increase the input size, or we would like to find out the behavior of our algorithm by looking at its behavior with the change in the input size, right? Any questions? All right. but if you have, you can write down, but I haven't received any. Okay, so big O notation is going to tell us how fast an algorithm is, right? Does it tells us in seconds? Yes or no? No, right. It doesn't tells us in seconds, but it tells us the number of operations required or the rate of growth of an algorithm. This is what it is going to tell us, right? It tells us the number of operations or rate of growth of an algorithm. When we say rate of growth, this automatically means on the basis of the input size. So, for example, suppose you have a list of size n, simple search will require a check of each element. So, it is going to take n operations, right? Uh, for this, the runtime is going to be, or the big O for this is going to be n, right? And we are going to depict it by on. Okay, this is for linear search. So this what big on is telling us. It is telling us that our execution time or rate of growth is directly dependent on the input size n. As n increases, so increases the number of operations required, right? So if, for example, if 100 searches need 100 milliseconds, then 1000 searches will require 1000 milliseconds, and 10 to the power of 6 searches will require 10 to the power of 6 milliseconds, and so on and so forth. So this is telling us that the rate of growth of our algorithm is directly dependent on the input size, which is n, right? Uh, Similarly, if we look at the binary search and we try to write down its big O value, then it is going to be O. Anyone? For binary search, like for linear search, we wrote down log n. For binary search, we are going to write down, yes, very good, log n, right? So this indicates to us that as the number of input, which is n, increases, the rate of growth or the number of operations which are required by our algorithm are going to increase log n, right? As n becomes, if n is 10 and we need 1 millisecond, if one is, this is 100, we'll need 2 milliseconds. If this is 1000, we'll need 3 milliseconds, and so on and so forth. Sorry, this is actually log base 2, so they are not exactly, but you can write down the log base 2 values. But the point is that as the input grows, the number of operations required are going to grow uh, in what? Proportion to log n. Perfect. Any questions? Anyone? All right. So no questions. Now, a very important observation which we are going to look at. Big O establishes a worst case run time, right? Worst case runtime. So while we say that ON, we are saying that this is the worst case scenario. It is not. There's a possibility that your algorithm for one search takes 1 millisecond, for two searches takes 2 milliseconds, for three searches take 3 milliseconds, and your some other searching algorithm, this is linear search. There could be some other searching algorithm which also takes something like this, but later on, when we need to do 10 to the power of 6 searches, this is going to take 10 to the power of 6 milliseconds. But other friend of ours, this guy, green one, he will take only maybe 10 to the power of 2 milliseconds, right? So we are looking at the worst case runtime. What is going to happen if whatever we are doing happens at the end of our strategy, right? For example, if we are searching for something, what is going to happen if what we are searching for is the last element, right? So if we do linear search, it's going to take on. If we do binary search, it is going to take log n, right? These are the worst case runtimes. We have very soon we are going to look at other notations as well, and then we will compare big O with the other notations. But for big O notation, we should always remember that it is the worst case run time for our algorithm. Okay. Any questions? Perfect. So let us look at this a small mathematical way of representing and calculating the value of big O from the mathematical expressions. Now, as we discussed, I think whenever we had the last lecture or the last to last lecture, we said that whenever we are writing down a program, especially engineering program or some other programs, what we are doing is we are converting a mathematical quantity other than maybe machine learning, where we are not directly converting the equations into loops, etc. But otherwise what happens that we have a set, we have an equation and we turn it into a program, and whatever results we get from this equation we are going to get from this particular algorithm, right? So this is what in general happens. So keeping this in mind, we will look at this slide. So big O notation for a function fn for which we are trying to write down a program. Uh, Big O fn is going to denote a function. So here it is OFN. It is going to be equal to Gn if there exists C which is greater than 0 and n naught such that uh, Gn is less than C into Fn for all values of n greater than or equal to 0. What does this mean? Uh, uh, just read it once more slowly and then we will try to understand what does it mean. This is the mathematical way of representing or telling about what big O notation is, right? And we know that for a computer engineer like you, it is important to understand the mathematics behind these operations or these notations, etc., so that you will be able to apply them anywhere, right? So, what is big O notation? We say that for a function fn, right? Whenever we say a function fn in computer science, we are actually talking about the program which is going to realize our function fn, right? OFN, which is big O, or the number of operations required to calculate or execute the function for Fn. So OFN is going to denote a set of functions, right? And why are we saying this? Because why are we saying that it denotes a set of functions? The reason is that to find out the value of Fn, we can do so by different strategies, right? Like in the previous case or the previous example which we learned, if for example our Fn is searching strategy, we can utilize linear search, we can also utilize binary search, we can use either of them, and there are other strategies also. So when we say OFN denotes a set of functions, so these set of functions are those functions which we are going to finally utilize and create our program. So what is OFN? It is going to be equal to GN, where uh, Gn is now from here, it says that OFN is equal to Gn. Come over here. What is Gn? Gn is less than C, less than or equal to C dot Fn, where C is some quantity which is greater than 0, and this happens for all n's which are greater than n naught, right? So we say that this is going to happen in such a way that n naught is, I mean, gn is less than or equal to c dot fn for all values of n naught where n naught is greater than n, which means that as greater than or equal to n. So this is going to indicate that c is a positive value, right? It is greater than 1. So gn is either going to be fn, which means that if we use some crude strategy to apply the algorithm, if we, for example, linear search, if we use some other strategy or a methodology which requires us to perform the task intelligently, then this gn could actually be less than fn, right? This could be less than fn for all values of n naught, which could be greater than or equal to n. So this means that n can increase to whatever value. This gn is always going to be either less than or equal to c into fn, where c is a positive quantity. In the next means over here, we will see that c is we are going to see that this c is not going to make much difference because it's a constant value. So in big O calculation, we generally remove them. But the point is that this gn, which is the value of OFN, is either going to be equal to Fn, where we use simple strategy to execute and find out the value of Fn, or it is going to be less than the value of Fn. For example, in binary search, as the input increased, the number of calculations which we have to perform was not increasing linearly. Therefore, in that case, the value of big O was not directly proportional to Fn. Now let us look at this function. So for example, this is what we are trying to you know write down as a function. So we are going to, so this is the value of big O, right? We say that our function is OFN. So we are going to write down O, and we are going to 5n log n plus 8n minus 200, right? Now, to find out the exact value of this big O, these constant calculations doesn't come into the picture. Why? Can anyone tell us why these are not required? Because irrespective of how we calculate or how we realize the function, these are always going to happen. They have nothing to do with the input size, whether input size is 1 or input size is 1 lakh. We always have to deduct to value 200. So it's part of function. We can, in finding out the final value of big O, or in simplifying this, we should always remove these constant values. Now, amongst these two, we have 5n log n and sorry, 5n log n, and we have 8n. Suppose now, please listen to the question carefully, and then you will be asked to answer. This is expression number 1, for example. This is second part of our expression. Out of 1 and 2, which is going to increase faster than the other, right? Out of these two, 1 and 2, which is going to increase faster than the other? Okay, I have received few replies. 1 and 8n, first n log n, 5n log n, 1. Okay, so many of you have answered correctly. One is, I think, slightly, he or she will be able to understand what we are saying. It is going to be 5n log n. And the reason is that, 5 is not required because we are trying to find out the growth. In growth, these constant values doesn't appear. So we have n log n, and we have n. So you can see over here that the first quantity is n, and then we are going to have a multiplication sign multiplied by log n, right? Log n. In the second case, we have only n. So we also know, got it? Perfect. So for others who haven't answered, I'm pretty sure that they were not able to understand. That is why they did not answer to the question. So in this case, as you can see very clearly, that n is multiplied by a constant value, whereas over here we have only n, right? And this value is always positive. Therefore, this is always going to be more than this one, right? And therefore, the growth rate of this part 1 is more than the growth rate of part 2. Growth rate of part 1 is more than the growth rate of part 2. In While we are trying to find out the value of big O, we are going, and we know from our previous, just now we said that O is going to tell us about the growth rate, right? So although we have 5 n log n plus 8n, but still we can see that since this is going to grow faster than this one, therefore overall growth of our program, or the execution time of our program, will be more dependent on this. And thus, this is what big O for this program is going to be, right? This is the intuitive explanation. Now, mathematically, what we can do, 5n, this is less than 5n log n plus 8n, which is going to be less than, this thing is going to be less than this because, because we know that in this case, because we know that in this case, 8n is growing slower than 8n log n, right? Therefore, we have used this sign over here. And then we combine them together, we got 13n log n. 13 is not there because it's just a multiplication factor. And the value of big O becomes n multiplied by log n, right? This is our value of big O, which you can deduce like this also. If there are multiple parts of a function, then we are going to look at only for those parts which are, anyone who can complete my sentence, I will repeat. If we have multiple parts of a function for which we are trying to write down the program, the value of big O will depend only on those parts which are, at least one of you, yes. Yeah, anybody else? Yes, it is going to depend only on that part whose growth is highest, right? Highest growth, or which is growing fastest, right? So your answer is absolutely correct. Uh, Maximum growth rate of time is more, right? Increasing with more rate, taking more time. Absolutely right. All of you are correct. So did you get it? Any questions? So you understood how we calculate the value of big O? Okay. So I hope that no. All right. So one of you has. So can you let me just quickly give you a glimpse of what we are saying. We are saying that if there is a function for which we are trying to write down an algorithm. Let me just clear everything so that we can quickly have one or two of you have wrote down that they have small doubts. So what we are saying is that the big O value of our function is, the big O value for our function is going to be OFN, right? And when we try to calculate this OFN, this will, what we are saying is that, for example, if this is equal to Gn, this Gn is always going to be less than or equal to C dot Fn. Now, to understand it through an example, we looked at this example, right? We said that this is the function. So this is our Fn, and we are trying to find out the value of big O for the program which is going to calculate, or which is going to take this much amount of time. Now we say that this is always going to be less than or equal to 5n log n plus 8n, right? And the reason is that, we have removed this whole thing from here. Therefore, this becomes, so this is going to take less amount of operations. Therefore, we get a 5n log n plus 8n. And then what do we do? from our this thing of mathematics. This is less than or equal to 5n log n plus 8n log n. Why this is less than or equal to? Because we know if we write down 8n and if we have 8n log n, then 8n log n is going to grow faster. And the reason is that in this case, in the second case, we are multiplying, we are multiplying 8n, which was over here also, with some positive quantity. So obviously this quantity is always going to be greater than 8n. Therefore, we said that we wrote down n log n by looking at this, and then we simplified both of them to this function. And then we said that 13 is a constant value. It does not make any difference, because while we calculate the value of big O, we are only interested in how the input values are going to increase. Therefore, the value of big O is going to be n log n. Now, this was mathematical way of explaining the things. We can always also look at the intuitive explanation of it, right? We say that this is our Fn, or the number of calculations which will be required to execute our function. And there is one question. Just a second, let me read it. Uh, okay, so one question, that if over here, in place of, we'll take this question in 1 second, right? Um, I will not forget, just remind me if, in case I forget. I won't, although. So the point is that, 5n log n plus 8n minus 200. So, in this case, this minus 200 is not dependent on n. It means that irrespective of how we write down our algorithm, this is never going to make any difference in the growth of function, right? This is what we said. We said that it depends on the rate of growth of algorithm, right? So this is not going to make any difference in the growth, because this is not dependent on n. So we can remove it, right? This is then, in that case, once we remove it, we got only this, which is uh, less than the value. So, sorry, which is the growth rate, which is only dependent on n. After that, we look at, so these are constant multiplications. We remove them. Then we are left with two expressions which are going to be required to make the final calculations. This is 1 and this is 2. One is n log n, second is n. And if we write down a program in that program, or in that, and write down an algorithm, in that algorithm, the growth is going to be dependent on this as well as this both. And then we are going to add them together. So if, for example, one growth rate is something like this, and there is another growth rate which is like this, for the same algorithm, right? When we say growth rate, it means that as n increases, the number of calculations which one part of our algorithm takes is going to increase like this, whereas the increase in the other part of the algorithm is going to be like this, right? This is both of them are dependent on n. Therefore, if we would like to make an overall assessment, we can always say that this one is the one which is going to tell us what will be the overall growth rate, right? Because this is very slow guy, so it does not make any difference uh, how it is increasing. If this one part of the algorithm increases very fast as we grow the values of n, then for our own approximation, we will say that the overall growth rate of algorithm is this growth rate. So what do? We find out that part of the algorithm which is uh, which is growing fastest, and that part of our expression is going to indicate our what the value of big O is going to be. So think of it for one or two maybe minutes, and then let me know if you understood it now or not. By the time I'm going to take another uh, message. If in place of minus 200, which is over here, in place of minus 200, we have plus 200, then less than sign, which is over here, will it be replaced by a greater than sign? Well, from mathematics point of view, you are right. But we should remember that what we are trying to do over here is we are trying to find out the rate of growth, right? So when we are trying to find out the rate of growth, in that case, these plus and minus signs do not make any difference. All we are interested in whether a particular part of our function is dependent on n or not, right? It can be dependent or it cannot be dependent. If it is not dependent, then we can quickly remove it. If it is dependent, in that case, we have to keep it there only, right? So now from mathematics point of view, you are saying that if in place of minus 200, if we had plus 200, then obviously when we remove it, this is going to increase or decrease. This was the original question of one of our friends, and he says that if in place of minus 200, we replace it with plus 200, and then when we remove this, so is it going to be a greater than sign or not? You tell me. The point is that over here we are reducing something, whereas in this case we are not reducing anything. Therefore, this seems to be a greater than sign. But even if we replace this part with a greater than or maybe equal to sign, then when we multiply this log n over here, this sign will change to less than or equal to. Now, this whole thing depends on many quantities. Uh, as far as this first line is concerned, mathematically, what you are saying is correct. But over here, what we are trying to do is we are trying to find out the rate of the growth of our algorithm. Therefore, whenever we are going to, so you actually don't have to look at this portion at all. We just have to look at to reduce the complexity of understanding. We just have to look at this, right? Now, the question will come whether this is still true or not, because we have removed minus 200 and we have replaced it with plus 200. And over here, we have multiplied with log n. So the question of whether this is true or not will depend on the value of n, and we know that we are going to consider the growth. Therefore, we are going to actually consider big values of n, right? For bigger values of n, this 200 or 2000 will not make any difference, and therefore we can always say that this is going to be less than or equal to the previous sign. We have another question. Okay, yes. It's a very important course, and I think books are very important to understand many a concepts. You will see that when companies come, they are going to ask you if you have clear concepts in data structures and algorithms. This is going to help you quite a lot, right? So my recommendation is that you slowly, it looks very big, but if you have read the Fountainhead, it's also 1000 pages, but you can always finish it maybe 2 3 months. So go slow, but be steady. Slow and steady wins the race. So you start reading the book, and when you read this book, I don't want to be preaching here, but when you read it, if you every day you read few pages, then you will see that very soon your initial log and growth rate of reading will drastically change to e to the power of x, right? So you will be able to finish it, right? Does it answers to your question? I think books are very important and you must read them. Okay, so all right. So did you understood it now? I mean, few people who wrote down that we are not able to understand. Oh, time is over. Oh, sorry. So just one more second. Just 1 second, sir. All right. So any questions? Okay. This Thursday is, I think, I believe that it's a holiday this Thursday. And Friday, sir, what about the notes? You have to make the notes and share it with me. So, this Thursday is possibly a holiday. I don't know. I will check the calendar. If it is not, then we'll have the class. Otherwise, Friday class will not be there because I will be on leave on Friday, right? So if Thursday is not 11th of March is a holiday, and so we'll meet on Monday now, right? Thank you, everyone. Goodbye.